Okay, so we're going to start here with chapter 1, and as we talked about, I think last time as well, again, the book is structured a little bit different than maybe a traditional sort of textbook. We do start with sort of the atom and all about sort of the atom, its structure, the experiments that came to help us understand the structure, protons, electrons, and neutrons. Then we jump right into sort of electron configuration, all that kind of stuff, and then we sort of go backwards after that a little bit. So it is what's sometimes referred to as the atoms first approach when we kind of talk about that. So when we talk about chemistry in general, chemistry really is sort of the study of matter, and really the study of matter and how it sort of changes and maybe even resists changes. And when we think about what happens on the atomic level versus, say, the macroscopic level or a macroscopic level, which is what we can kind of see. Sometimes when we see something happening, for example, in a reaction, it may very much look to us like the reaction is over. There's not much happening. So, for example, if you poured a couple of solutions into a beaker, and at some point maybe that started like at a red color and then it sort of ended at like a colorless sort of color. And on the big level there, when you look at it, it may just look like, nothing's happening anymore. It's all done. The reaction is complete. Now, on the microscopic level, if you were able to sort of zoom in there, this could be a reversible type reaction. And in a reversible type reaction, it basically goes in both directions from the reactants to the products. So although once it reaches something like chemical equilibrium, it may very much appear on sort of the big scale there as being sort of static, everything's done, nothing's happening. But if you were to sort of zoom in there, there is a lot of activity that's happening. You have reactants going to products, you have products, which is the stuff formed in a reaction, going back to reactants. So you have really a lot of activity. And in a case of something like chemical equilibrium, which you'll touch upon a lot more in Chem 200B, because that's pretty much all you talk about in that class. But in terms of chemical equilibrium, they basically are going in the opposite directions at the same rate. So just as fast as you make those products will recombine and go back the other way. So basically everybody sort of locks themselves into sort of where they're at that point. And again, just looking at the beaker, it may appear not much is going on at all. But again, there's a lot of activity that's really, really happening. So when we talk about chemistry, again, really matter is sort of what we look at. And when we talk about matter, there really is sort of three states to matter. Matter is really anything that occupies space and has mass, which is pretty much everything. And when we talk about sort of matter, there's really those three states of matter. And we have things that are in the solid state. And in the solid state, things are pretty much packed in there, pretty tight to one another. They really don't have a lot of energy associated with it, right? So they kind of lock themselves in. And that's why when we think of things that are solid, they are rigid, right? They're very hard to change. We also have the state of matter, which is liquid. And in the liquid state of matter, we still have things relatively close to one another. But the main difference here is it does have a lot more energy, if you will. So there's more energy associated with it, which means they actually do have enough energy to sort of slide by each other, the atoms, the molecules, and stuff like that. So when we think about things that are liquids, right, they flow. You could pour them, and that's because there's a little bit more energy. They can kind of move past each other. You could pour and make a mess if you like. When we get to the gas phase, at that point, everybody has really completely broken apart from one another. So they have completely broken apart from one another. They're flying around. Obviously, they have a lot of energy at that point. And as we'll talk about, obviously, when we get to the gas chapter, obviously, as they're flying around, there's going to be numbers of collisions that's going to occur as those gas molecules fly around. And that's what we associate pressure with. So obviously, more collisions, more pressure, less collisions, less pressure. And a lot of what we look at in terms of chemistry, oftentimes we'll deal with matter and really, sort of the transition of matter from one state to the next. For example, if we were to, here, I think I'll draw it up here. So if we were to take a look at these three states of matter, our solid, our liquid, and our gas. There's also transitions that occur. So for example, as we go from solid to liquid, that is the process of what? Yeah, that's the process of melting, right? If you took an ice cube out, right, it will start to melt. And if you go from liquid to solid, that's the process of freezing. Going from liquid to gas, that's the process of evaporation or vaporization. Going from gas back to liquid, that is condensation, right? So we kind of have to cool down it. We also can go from solid directly to gas and skipping the liquid part, and that is what is referred to as sublimation. That's like dry ice does that, right? Dry ice, as you might know, right, is not water. It's actually carbon dioxide, and it basically goes from solid to gas, skipping the whole messy liquid middle stage there. We also could go the opposite way there. Gas back to solid, also skipping the liquid phase along the way. And that is what is referred to as deposition. Maybe you're old enough to remember DVD CDs. If not, I could Google it. But they're shiny, and that's how they get them shiny. They deposit metals on them and stuff like that. I just heard on their radio, Netflix, I think, right? They're not going to send out any more DVDs anymore. I didn't even know they still sent out DVDs. I was kind of surprised. So a lot of what we look at in chemistry involves these sort of changes of state, and really tied to a lot of things that we look at in chemistry and sort of chemical reactions is really tied to energy. So although they kind of take energy out of this class and we don't officially talk about energy or do the energy chapter, as I mentioned, I think the other day, there definitely will be a lot of mention of energy in these chapters because they assume that you did that chapter, but you will do that chapter next semester. But we will talk about some energy, but let's talk a little bit about the energy associated with these processes. As I go from solid to liquid to gas, does energy need to be put in or removed in those processes? What do you think? It's 50-50 shot. Yeah, energy does need to be basically put in or absorbed. If you think just simply about the ice cube example, right? When you take the ice cube out, it's basically picking up all the heat and energy from the air, right? And it's going to start to melt. You want to make some pasta or something like that. You take the water, right? Put some flame underneath it to start to boil the water, which will heat up the water and go from basically liquid water to gas, which is the steam that you see there. So all these processes in this order, going from solid, liquid to gas, those are all processes that absorb energy. And in chemistry, any type of process where energy is being absorbed is what's referred to as a endothermic process. So when somebody says this process is endothermic, that means that somebody is basically absorbing energy. Obviously, if we sort of rolled in the opposite direction here, if we went from gas to liquid to solid, in this case, energy has to be removed. And if you just think about it, gas molecules have a lot of energy. That's really why they're flying around, right? They got all that energy, so they're flying around. So as they're flying around, if you remove the energy from them, they're not going to fly around as fast, which means when they come in contact with others, they no longer have enough energy really to escape each other. They kind of stick, if you will, and they kind of drop into the liquid phase. And if you continue to sort of remove the energy from that process, they're just going to kind of lock in a little bit more there and not even have enough energy to kind of pass one another. And then you will sort of lock into the solid stage. So as we go from gas to liquid to solid, these are all processes that basically release energy. And in chemistry, when we do anything that basically releases energy, that is what is known as being exothermic. Now, again, although we don't really talk too much about energy, we'll talk a little bit about it at the end here in this chapter. One way in chemistry, and very commonly done, that energy is sort of represented in reactions or chemical reactions, is by what is sometimes referred to as delta H, and that is the change in enthalpy. It's kind of a fancy word there for basically kind of the heat of the reaction. So how much heat is either generated or absorbed when a reaction takes place. And typically speaking, I'll spit that out, I think. Typically speaking, whenever you sort of calculate any type of energy calculation, be it delta H, or maybe from the previous class, you remember specific heat where you calculated Q and stuff like that. If you calculate any type of energy value and the value is positive, that usually represents a endothermic type of process. So if you see a chemical reaction and they give you the delta H value for it, and again, the number really doesn't matter all that much, it's really just the sign of it, and the sign is positive, then it will be an endothermic type of process. And opposite of that is a process where it is negative, represents a exothermic type of process that occurs. So if you have any type of energy value that's either given to you or you calculate it and it's a negative sort of value, that definitely is an exothermic type of situation that's occurring. Any questions on any of that there? While we have this up here, the double jeopardy question is, melting and freezing, does that occur at the same temperature or different temperatures? It does occur at the same temperature. So melting and freezing occurs at the same temperature. So does evaporation and condensation. For example, something like water, 0 degrees, write that right there, write it right there, 0 degrees Celsius is its normal freezing point, melting point. And at 100 degrees Celsius is the normal boiling point there for water. And it happens exactly at 0 degrees Celsius, for example, for water. At 0 degrees Celsius, you actually have both phases happening at the same time. You got kind of like ice crystals. So you got a little bit of solid ice, you got a little bit of liquid water sort of happening exactly at 0 degrees. It's really not until you get above 0 degrees that you kind of really sort of transition into liquid water, or a little bit below 0 degrees that you get into ice. And the same thing happens at 100 degrees Celsius. You basically have both phases happening at the same time. So you have liquid water and you have steam happening. And again, not to get a little bit above 100 that you truly sort of transition, and not below 100 that you're kind of go backwards there into the liquid phase. Now, what determines what happens in terms of, you know, which way you will go at, say, 0 degrees or 100 degrees, it really is the energy component that determines sort of which way you go. So if you're at 0 degrees Celsius and you continue to put energy in, you will continue the process of melting and go over to liquid water. If you're at 0 degrees Celsius and you take basically the energy out, like throwing it into the freezer where it will basically take out all the energy, you will then go the other way and it will start to freeze. Any questions on that there? Okay. Go back to kind of what I skipped over, I suppose. All right, side tangent. All right, we'll come back here. So matter obviously is really represented by atoms or molecules. And atoms are really, as we'll talk about, the basic unit of any element that can really enter into sort of chemical combination. An atom is the simplest unit of an element. Obviously, the periodic table has all of our elements. As you may know, and as we'll talk about, obviously atoms contain protons, electrons, and neutrons, right? So they contain all those guys. Now, a molecule is a combination of two or more atoms that basically come together. And oftentimes people have a question of, you know, molecule and compound, for example. So let's talk a little bit about a compound. We'll add that to the list here. A compound is the combination of two or more atoms from different elements coming together. So two or more atoms from different elements coming together is a compound, and that is in some cases different than a molecule. And it does depend. So we have basically elements, which are the basic unit of everything. So we could think of elements as kind of like the alphabet. And obviously, I think in the alphabet, we had 26 letters still, I hope. We have only so many elements. But just like the alphabet, different combinations of those letters, right, give you different words, and different combinations, obviously, of elements give you different compounds that you can form. Now, in terms of elements, molecules, and compounds, there are a few things just to try to keep it straight. I'll get rid of this here. Now, there are certain elements that are molecules, and that is naturally how they come. They're sometimes referred to as diatomic, which means two atoms, molecules. And that is your hydrogen, your oxygen, your nitrogen, and by the way, most of these are gases, fluorine, chlorine, bromine, and iodide. So that is naturally how each of those guys basically come when they're by themselves and they're not combined with anybody else. Now, they are molecules, but each of these guys here are also elements. These are all elements because, frankly, they're the same element attached to each other. So hydrogen comes like this. Oxygen comes like that. Nitrogen comes like this. So they basically come as twos, but they are all the same element. So they're both hydrogens, both nitrogens, both oxygens. So any one of those guys would be classified or could be classified as an element. They could also be classified as a molecule. They cannot be classified as a compound because there's only one element involved in each of those. So now if we had something like water, well, H2O action here, that obviously is hydrogen and oxygen together. That is definitely two different elements that are together. That means that this is a compound. Is water a molecule? Water is a molecule because there is two or more atoms together, so it is also a molecule. Is water an element? Water is not an element. Again, here we have hydrogen and oxygen. So you could think of a molecule as really just like a basic definition of, can be two or more atoms together, that's a molecule. Could be two or more of the same, two or more of different ones, those are all molecules. But in order for it to be a compound, it has to be different elements coming together. Any questions on the difference between those things? All right. So obviously as well, when we do write formulas, which I think is what the previous slides showed, that I kind of scribbled over. We do use subscripts, by the way, when we do write them. Just a reminder that these subscripts, and if there is nothing written there, it is assumed to be one of something, right? And we typically don't write one in chemistry a lot for anything. So it's not a zero of that. So basically this means in something like water, the number always goes to the guy to the left. So there's two hydrogen atoms, right? And one oxygen atom here in water. A chemical reaction is written with an arrow, And in this case, this would be something like our decomposition of water, electrolysis of water. You basically start with some water, run electrical current over it, and you can break it back down into its elements. So a compound, like we see here with water, can be broken back down into elements, which each of those guys are, the oxygen and the hydrogen. But once you get to elements, that again is as far as you could go back. So you cannot break elements down into anything else. Any questions on that there? Yeah. 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 So in this case, what will actually happen is I'm going to do a really bad drawing. You'll see why I failed art a lot, but but you could actually do this experiment. Actually, class I teach, they actually do this experiment where you basically do electrolysis of water. All you need is like a 9-volt battery and some electrodes, basically. But basically, what happens in that situation is, for example, if you did have the water and you put some electrodes in there, a lot of times if you do this experiment, or if you don't sort of do it as an experiment, they'll put like little test tubes over the electrodes. And when you run the electrical current, what happens is you're going to create these guys, which are gases. And that means the gas is not going to stay in the liquid part, which means it's going to, in the case of if you did it as an experiment, it would end up in like the test tube. So you'll see this like empty area in the test tube is where the gas is. If you didn't have the test tubes, obviously the gas would just escape the beaker or whatever it may be, stuff like that. And it would then obviously combine with air, or it would be blown away, which is why they don't come back together at that point. Yeah. Other questions? All right. Let's talk a little bit about the scientific method. The scientific method is used a lot in chemistry and in science in general. And really, the scientific method does really usually start with some type of observation that occurs, some type of observation, and you go, or most likely whoever you work for goes, I think that's kind of interesting. That means that's your job now to go figure that out. So you make this observation, and usually what you try to do is come up with a hypothesis, right? And usually a hypothesis is a good hypothesis, is sort of a testable sort of explanation of maybe what you're observing. You know, ideally, usually in science, you want something that you could kind of do some type of test to either maybe verify what you think is happening, or try to hopefully lead you to what could be happening. So you get this observation, you have this hypothesis, and usually you would then perform some type of experiment. And in most cases, as you do the experiment, that usually will lead to, some might say, a vicious circle of, hey, there's some more observations that you occurred. And then you go tell your boss, and they go, cool, go do some more tests. And then you maybe have to revise your hypothesis and do some more experimentation. And, you know, this kind of circle that will continue. And at some point, though, what you're sort of hoping to reach is really one of two things, maybe a theory or a law might come out of it. And the hope of your sort of experimentation is for you to have sort of a better understanding of that. And there is sort of a difference between a couple of those things, which is a law and a theory. So we'll start with a theory. A theory is something that at the point of you sort of proposing the theory or the model sort of is an attempt to really explain what you're seeing. Now, in a theory, it may mean that over time, your theory may be proven maybe not so correct, or maybe some parts of your theory may be proven not so correct. And so, for example, the Dalton's atomic theory, there are some parts, as we'll talk about, Dalton's atomic theory, which, you know, are correct still. And there are some parts that were later proven not to be so correct. Same thing with like the idea of the Bohr model. Our theory of the hydrogen atom works really well for hydrogen, But as you move away from hydrogen, doesn't work so well in explaining sort of the things that you see. So theories, in a sense, are not necessarily set in stone. They are things that will not always 100% always, sort of check out no matter what the situation is, can be revisited, sort of revised. Now, a law, on the other hand, a law is something that basically summarizes what happens, but pretty much it always happens. Yeah, so it's like it always happens that way. It's sort of proven, I guess, proven not to be disproven, I suppose, in the sense, like the law of conservation of mass, right? So when we start a reaction with our reactants and we make our products, we have conservation of mass, which means we don't lose anything along the way in a chemical reaction. All we have are things being rearranged. And that means if you started with like 4 carbons on the reactant side, you should end up with 4 carbons on the product side. They may be in different compounds on the product side, but you will still have the same amount of carbons on sort of the starting and the ending. And since carbon has the same mass on the left-hand side or the right-hand side of the arrow, you will have that conservation of mass. Same thing with like the law of conservation of energy, right? We don't create energy nor destroy energy, but energy is thought of as being sort of a nice, perfect transfer of energy from one place to the next. So typically with energy, we think of it as, this kind of nice, perfect sort of transfer of energy in a lot of cases, which means that if something sort of releases a certain amount of energy, there has to be somebody else that's going to basically pick up the exact same amount of energy. And that's why when we talk about or do sort of energy calculations, the amount of energy that's released will be really the same amount that's absorbed. The way that we sort of signify what's happening is, as we talked about earlier, the sign of those values. So one would be negative for the one that's releasing the energy, and then one would be positive that's sort of absorbing it. So somebody releases minus 75 kilojoules of energy, the surroundings there will pick up positive 75 kilojoules of energy. So there's this sort of nice exchange. Same idea with the classic potential kinetic energy sort of definition, right? The big giant boulder on top of the hill, right, has a certain amount of potential energy as it's about to sort of come over the hill. Hopefully nobody's standing below it. But as it goes over the hill, right, it transfers to kinetic energy, energy of motion, and then it plops down, right? And it then has a new potential energy because it just transferred all that energy to the ground, right? So that energy is accounted for in the ground. And hopefully, again, nobody's standing underneath there, or they would pick up that energy along the way. So something we don't do in this class anymore, with energy, but you'll do in the next class, something like Hess's Law, maybe you talked about, maybe in the first one, where it doesn't really matter in terms of energy, in terms of reaction, how many individual steps it takes to go from like point A to the end. Not all reactions happen in a one-step situation where it goes from reactants to products, one and done. Lots of reactions, just like one reaction, then that guy reacts, and then another one reacts. And we can figure out the total amount of energy that occurs in those type of situations simply by just adding up each of the parts there, because there's that sort of conservation of energy. Any questions on any of that there? Yeah. All right, so now we're going to talk a little bit about the atom, and we're going to go through some experiments that helped us sort of understand the structure of the atom, and let's take a look at it. So originally, pretty much everything was thought of by philosophers and so forth, that, everything's made up of these small, sort of indestructible sort of substances, which was referred to as atomoses. And obviously that's a forerunner to atoms. Robert Boyle did a lot of quantitative type experiments. Quantitative means measurements, right? And qualitative means like observations, right? So quantitative, he did a lot of those experiments. And there's some important sort of laws that sort of came out as we kind of went through certain processes to understanding the atom and sort of an early sort of theory about the atom. One is, as we sort of touched upon there, the law of conservation of mass. And again, mass is neither created nor destroyed. and you do have that conservation that will occur. I think that will play here, but if you did a chemical reaction, you can actually measure, all your reactants masses and all your products masses. So if you were going to take two solutions and pour them together, you could put them all on a balance together and make sure they're not mixing, obviously, yet. And you can get the mass of everything that's going to come together. Then you can mix them together, put them back on the balance after the reaction is done, and you'll have basically the same mass. So as we saw there in the video, he was able to show that he had the reaction that occurred at the end. And again, what we started with and what we ended with basically had the same mass. And again, that's the idea that we were talking about, that, however many carbons we start with, we will end with, basically the same amount of carbons. Now, when we look at this, another important sort of law that came about is the law of definite proportions, which was done by Proust. And basically what he said was that if you take a certain mass of one element that sort of combines with another element, you will always have the same sort of ratio that's present, no matter really where that substance comes from. So, for example, if we had something like water here, no matter where you get that water, you get it out of the faucet, you get it out of a nice bottle, you get it out of a bottle they charge you at a restaurant, $50 for nice purified water, sparkly, whatever it may be. It's still basically H2O, right? So it's still basically made up of 2 hydrogen atoms for every 1 oxygen atom that you have. And again, no matter where it comes from, no matter how much of it you have, you got like a little container of water, you got a giant container of water, they're all basically H2O. And because, for example, the mass of hydrogen is about 1 gram, just to round a little bit, 1.008, and the mass of oxygen is about 16 grams, that basically means that for every water that you have, you basically have 2 grams of hydrogen for every 16 grams of oxygen, which if we reduce that down, that basically means that for every 1 gram of hydrogen, you have about 8 grams of water that basically comes. So no matter where you get it, no matter how it's derived, if it is fundamentally water, that is basically the ratio that you should always have in that particular substance. Any questions on that there? That would also mean, for example, that if I had, as we can see here, 2 grams of hydrogen, I should expect, as we see, 16 grams of oxygen, right? If I for some reason had 4 grams of hydrogen, I should expect to have how many grams of oxygen in this case? Yeah, I should have about 32 grams of oxygen. Again, that's basically 4 times what I should have there. So 4 times 8 would give us the 32. So, if it is sort of that substance, that's really the ratio by mass that you have of those elements. That is really what you should expect to have. Any questions on that? Now, another important law is the law of multiple proportions that was done by Dalton. And basically what Dalton said was, when 2 elements form a series of compounds, the ratio of masses of the second element, when it combines with 1 gram of the first element, will always end up in basically a kind of whole number. So, for example, if we have something like CO and CO2, those are both carbon basically and oxygen compounds, right? And they're both made up basically of the same 2 elements, just different amounts of each of those. Now, in this particular case, we can look at it, and again, carbon is a roughly 12 grams. We'll just kind of use a whole number here. Again, 16 grams for oxygen. And in this case, we have 12 grams for the carbon that's there. And here we actually have 2 oxygens, which would give us our 32 grams basically of oxygen that is present. So what it's talking about here is we want to really know kind of the ratio of how much of one element we have to like kind of 1 gram of the other element. So in that particular case, what I'm going to do is I'm going to divide, so I'll get maybe a whole number-ish or a larger sort of number. I'm going to divide by the smallest number of grams in each of these. So if I do that, I originally had basically 12 grams of carbon for every 16 grams of oxygen. And if I divide everybody by 12 there, that means I have 1 gram of carbon will give me 16 divided by 12. Give me about 1.33 grams of oxygen in the case of CO or carbon monoxide. Again, basically just dividing everybody by carbon in this particular case. If we kind of do the same situation over here with CO2, and in CO2, we essentially have 12 grams of carbon for basically 32 grams of oxygen. We divide everybody by the 12 grams, so we are comparing apples to apples. Here we kind of did it per gram of carbon. We're going to do it here per gram of carbon as well. That would give us basically 1 gram of carbon basically gets us 2.67 grams of oxygen at that point. Any questions first off on that? So you may be looking and go, that doesn't look very much like a nice whole number. So what they're talking about now is comparing the amount of oxygen in CO2 to the amount of oxygen and carbon monoxide. So if I do that, basically in carbon dioxide, I have 2.67 grams of oxygen. I'll just put CO2 next to it. And in the CO, I basically have 1.33 grams of oxygen. And again, that is from the comparison to 1 gram of carbon in each of them. And if I take basically 2.67, or the real number, 2.666 all the way around, divided by 1.333, I essentially get 2. Right. And that is what it is talking about. The ratio here by mass is a whole number that we end up with. So essentially here, as you can see in this particular case, based on the grams of carbon, we kind of have twice as much oxygen sort of happening there in the CO2. But we do get this whole number ratio. Any question on that? And you can do that for any type of compound. You can do nitrogen and oxygens as well. The deal here when you're sort of doing or trying to prove is sometimes how the questions are worded, that it fits the law of multiple proportions is you basically want to take one of the elements and make it 1 gram and divide the other one by that grams and compare the non-1 gram to each other and see what the ratio is. And it should end up always as like a whole number sort of ratio when you compare 2 different compounds that contain the same elements. Yeah. Yeah, so here what we're looking at is, so what Dalton basically said in multiple proportions is that if you compare sort of the ratio of 2 different compounds, for example, that are made up of the same elements, the ratio of the same element in those 2 different compounds will always end up being like a whole number, or whole number ratio to each other. And that's why really here we normalize each of these to 1 gram of carbon, right? So here they're both 1 gram of carbon, but now we could really look at the grams of oxygen in this particular case. Now, if you perhaps did this and you didn't hit a whole number when you sort of, I can't think of one off the top of my head, but let's just say we sort of did a division thing like this, and we ended up with like, say, 2.5, for example, over 1 or something like that, basically. What you would do is basically you would want to find the next whole number sort of ratio that would get you to a whole number, which means in this case, obviously, you would need to multiply both of these guys by 2. And that would give you basically in that sort of made up one I just did, you would kind of have to have 2 of one to 5 of the other. That would be the ratio that you would need in that particular case. So you may, if you come across a problem, for example, like this, you may not get a nice, pretty kind of whole number when you do that. And you can sort of adjust it by sort of figuring out, what can you multiply both by to end up with a whole number? And that really comes down to something that you're probably familiar with as well, that obviously came out a little bit later on, but the idea that you can't have like a half atom, right? So you can't have like 2.5 atoms in a compound. So if you remember empirical formulas, molecular formulas, or something like that, you got to have whole numbers, right? And when we look at the subscript for a compound, you know, really these numbers has to be kind of whole numbers. So you got to have those whole number ratios of what's present, because you really can't just have like a half of something. Yeah. In terms of a formula, in terms of how sort of elements come together, they always really come together in whole number sort of multiples. So, you know, for example, you can't really have anything like, you know, H, you know, 1.502 or something like that, right? So you just can't have like a half a hydrogen hanging out, you know, by itself. So you do have to have whole numbers, you know, on both of these. And in this particular case, we got a nice ratio that in this case, you know, when we compare those two compounds, it does come up to basically a whole number, which sort of validates the law of multiple proportions. But sometimes it could be even an experimental sort of problem or something where they like, hey, experimentally they found this and this. When you go to do this division here, this part here, and to compare the same element in the different compounds, you may actually not hit a whole number, mathematically speaking. So in those cases, what you want to do is sort of think about a multiple that you can multiply that number by to get to a whole number. So in my made up example, you know, I did the division, I got like 2.5 rather than 2. So I know I can't have, it's got to be a whole number. And really what that represents is when these guys come together, they got to come together as like whole number multiples of each other. And that's why we would want to kind of adjust it up to like the 5:2 ratio would be the smallest combination in that case that, you know, they could kind of come together. Yeah. Yeah. Other questions? Yeah. So let's talk about Dalton a little bit more. He's an important guy. There we go. That was a good talk. I want to go back maybe. There you go. All right. So John Dalton, he was an interesting guy. He liked math. He would write down the weather report every day, like what the weather was. He never married, oddly. But he did like to go bowling on Thursdays, which if you learn nothing else in this class, that is what you should know. And I'm not kidding, really. You should really know that. Yeah. So it will be on every exam you take. So don't put Friday. Don't put a day that ends with Y. Don't put Cosmic Bowling Sunday or Saturday. So it is Thursday. But really, besides going bowling on Thursday, what he's really known for is he came up with this idea of basically the atomic theory of basically an atom and sort of the parts of an atom, not really parts of atom, but you know, sort of how an atom sort of operates. So let's take a look at each of these parts of his atomic theory. And as I mentioned before, there are certain parts of his atomic theory which were later found to be not so correct, and there are some parts that are still correct and stuff like that. He said that each element is made up of tiny particles he called atoms. There's also this idea of them being sort of indestructible. And as we'll talk about, that is something that was sort of later proven not to be so correct. And in the case of sort of regular chemical reactions, it is correct because we have that conservation of elements, like we've been talking about. If you start with 6 carbons, you end with 6 carbons. But in the case of like nuclear chemistry and nuclear reactions, it is completely different. In a nuclear chemistry or nuclear reactions, which you'll learn about in 200B as well, you have no conservation of elements. So you actually do nothing but change one element into another element in nuclear chemistry. So you can sort of create new elements and sort of destroy those along the way. They're not indestructible. You can sort of transform them. So that's one aspect of his atomic theory, which is incorrect. He also said that the atom of a given element are identical, and that atoms of different elements do differ in some fundamental way. This is also another excuse me, aspect of his atomic theory, which is incorrect. So the idea that atoms of a given element are identical, that all atoms of the same element are always going to be identical. And it was sort of the existence of what are referred to as isotopes that basically made that a little bit incorrect. And isotopes are the same element, but they have different masses. So obviously that would mean that they are not identical to each other, right? Those atoms, if they have different masses. So sort of the existence of isotopes does sort of disprove that part of it. But the other part is okay. You know, the atom, an iron atom is different than, say, a carbon atom or a copper atom and stuff like that. But we do have different atoms of the same element, which are isotopes. Some other parts of his atomic theory, and you should know the main parts here of his atomic theory, obviously. Chemical compounds are formed when atoms of different elements basically combine with one another. A given compound always has the same relative number and types of atoms. So sort of what we were just talking about a little bit with the multiple proportions and all that kind of stuff. You know, when they do come together, they do really come together in that same sort of mass ratio of what you would expect. And that sort of even different compounds with the same elements will have that same sort of whole number ratio of how they basically come together. He also said that chemical reactions involve the reorganization of atoms, changes in the way they are bound together, and that is true. Definitely in chemical reactions, that is what takes place. All that takes place in chemical reactions is simply we break all the bonds on the starting stuff and we reassemble everybody on the other side and make new bonds. So kind of break bonds, make bonds. We don't change elements or anything like that. So when we have a chemical reaction, which is what he's talking about there, that is absolutely true. We don't play with anything in the nucleus, as we'll talk about. So when we don't play with anything in the nucleus, we don't really change any elements along the way. And again, that's why we balance equations, right? To make sure we have the same numbers on each side. Any questions on that there? Atoms themselves are, again, as I mentioned, not changed in the chemical reaction because, again, all we are doing is simply breaking bonds, kind of freeing up the atoms so that they can recombine on the other side. All right, so which of the following regarding Dalton's atomic theory are still believed to be true? Elements are made up of tiny particles called atoms. That is true, yes. Second one, all atoms of a given element are identical. Is that true? That's not true. A given compound always has the same relative numbers and types of atoms. That is true. And atoms are indestructible. Not so true in that case. Yeah. So it looks like in this case, 1 and 3 looks like a winner, I think. Any question on Dalton's atomic theory? So you should know, obviously, bowling on Thursday and the other parts of Dalton's atomic theory, and obviously which ones are still correct and which ones are incorrect. Any questions on that? All right. Now, along the way as well, there's some other sort of theories that sort of came about and helped us sort of better understand how atoms and stuff come together. And we'll actually visit some of these things a little later on. Actually, these both sort of in the gas chapter when we get there. But Lukacs Law measured under the same conditions of temperature and pressure, the volume of a gas that react with one another. So basically, his law was kind of P1 over T1 is equal to P2 over T2. And basically what you saw as a result of his law is the thing changed, but here we go. As the pressure goes up, so does the temperature, and vice versa. The pressure goes down, so does the temperature. And if you just think about it sort of logically speaking, this, by the way, is at a constant volume situation. So it's basically locked into place. Those gas molecules are flying around. So as you increase the temperature, the gas molecules are going to fly around a lot faster, which is going to create a lot more collisions that's going to occur. And because that volume is locked into place, there's nowhere for them to go. So we would see an increase in the pressure that would occur. And opposite of that, obviously, if you kind of lowered the temperature, the gas molecules would be flying around a lot slower. It would take a lot longer for those collisions to occur, and we would see really a sort of drop in the pressure, right? Avogadro's hypothesis said, kind of interesting enough, if you're dealing with sort of a reaction that involves gases under constant temperature and pressure, basically you will have the sort of equal numbers of volumes to moles. So perhaps you're familiar with stoichiometry, I hope. We'll talk about it later on, but kind of like when you do stoichiometry, the mole to mole relationship. So if you had a reaction like N2 plus some H2, a little NH3 action, 2 there, Na3 there. So normally if we went through sort of this equation here as the sun hits it, we could go and use the coefficients and go, in this reaction, we have basically 1 mole of nitrogen, we have 3 moles of hydrogen, and we have 2 moles of ammonia, which again are just the coefficients, obviously, here in the valence equation. And we could say they're equal to each other, right? If we were going to do some type of stoichiometry problem, 1 mole of nitrogen would equal 3 moles of hydrogen. It's sort of the proportion, if you will, of what needs to come together for that reaction to sort of take place. Because at constant temperature and pressure, you could actually do it in terms of volumes, because the volume of it will be the same as the moles. So you could go through that equation. And for example, if you wanted to use like liters as your volume, you could say there would be 1 liter of nitrogen, and that would react with 3 liters of H2 to give you 2 liters of NH3. So Avogadro's law, under these specific conditions, that it's a sort of gas reaction that's occurring in all gases and is constant temperature and pressure, and kind of the moles that you got going on there is equivalent to sort of the volume that you got of each of those gases. Any questions on that? And we'll visit that more, obviously, when we get to gases. It is. So it would be a reaction where pretty much you have all gases sort of happening in that situation. And it's because really they're in the same container, right? And if you think about gases, we'll probably talk about it a little bit when we get there, but if you think about gases in a container, they can't escape, right? So all the moles of gas stay the same. And when we think about gases, basically we think about the container as sort of its volume and stuff like that. So they're sort of equivalent in that case. Other questions? All right, so here's our Dalton picture, different collections of compounds. And again, we could go through each of these and do our sort of multiple proportion sort of calculations. And again, if we sort of compared, for example, the amount of oxygen from this guy to this guy, again, we'll get some of that whole number that should come out when we do it, or even this way as well. So you could do those sort of calculations with any of these guys, and it should give you that whole number sort of ratio that comes out. So based on Dalton's atomic theory, there are several things that were sort of thought about in terms of the atom, and a lot of investigation sort of happened between the 1850s and the 20th century. And although it was known that atoms are really small things, they were found to sort of contain a internal structure, even smaller sort of particles. And these are sometimes referred to as subatomic particles. And you might be familiar with those. Electrons, protons, and neutrons are found in atoms. Just to get it up front and out of the way here, electrons are negatively charged, right? Protons are positively charged, and neutrons have no charge, right? So although these atoms, which basically are the basic representation of any element, are super small, they got this nice internal structure of even those smaller parts. So what we're going to talk about now are several experiments that sort of led us to sort of the better understanding of each of these particles and sort of how they were discovered, a little bit about each of these and maybe where they're located within the atom. So we're going to go through some of these experiments, and I'll kind of point out which ones obviously you should know and as we go through it. So a lot of the early work was really done by a guy named Thompson, and he did experiments using a cathode ray tube, sometimes referred to as a CRT. You might be familiar with cathode ray tubes, maybe. You could Google it with your DVDs and CDs, but older TVs that have like a big back, years ago, TVs weren't on the wall, they were on the ground, right? You call a TV repairman out to go fix it and open up the back of it. They have those older sort of TVs, not flat screens or plasmas or any of those type of things, are CRT type tubes, also computer monitors. If you've ever seen an older computer monitor where it has like the big back that comes out, that is a CRT type monitor. But Thompson did a lot of work with the cathode ray tube, and what he was able to basically determine from his experiments was the charge to mass ratio of an electron. And basically, the cathode ray tube was a tube, as we can see here, of basically negatively charged particles. And one of the main sort of things in chemistry that comes up a lot is the idea of electrostatic attraction. It's commonly referred to as opposites attract, right? So much like in life, opposites attract. You get two positive people together, they don't want to be near each other. Two negative people, they don't want to be near each other. But you get like a positive person and a negative person, you know, they sort of balance each other out and they're attracted to each other. So same thing in chemistry. If you have opposite charges, positive and negative, they are attracted to one another. But things with the same charge really don't want to be near each other, so they repel each other. So things that are negatively charged and negatively charged are positively charged and positively charged. They really do repel one another. But if you get something that is sort of negatively charged and positively charged, they are attracted to one another. And they can use this in a cathode ray tube because this particles that are negatively charged, there's actually a positive side to the tube and a negative side to the tube. That means that all of our negatively charged guys are going to be heading towards the positive side of the CRT tube. Now, a lot of times in the CRT tube, they'll put like a fluorescent sort of material on it, and you can actually see, you know, where it's actually hitting and stuff like that. Speaking of TV repairmans, I know we didn't just go to Costco and get a new one. You would call somebody, but they would actually have to sort of tune your picture tube and your TV and stuff like that. And here's an example: attracted or repelled. And that's very helpful when experiments are being done, because you can use something like an electrical field, right, to do things and affect charges. You can also use something like they did there, a magnet that has a south pole, north pole. It kind of works similar. You could kind of really affect it. So when we talk about sort of particles in these type of experiments, there's usually, if you had something like an electrical field, for example, and you had something that would say a negative plate and a positive plate, and if I shot a particle through it and it started to bend upwards towards the negative plate, I would know that that particle has what type of charge? The positive charge, right? Because it's attracted. Just like if I kind of shot it and it bent towards the positive side, right? I could make a pretty good guess that that guy would be negatively charged. And if I shot it and it pretty much just kind of sailed right through, that's going to be something that basically has no charge associated with it. So a lot of experiments, you know, they use things like electrical fields and magnets. They still do, and really taking advantage of sort of the charge of things to really sort of understand what's happening. So Thompson did a lot of this experiments with the CRT tube, and as I mentioned, what really came out of it was the charge to mass of an electron. And he found that the charge to mass of an electron was minus 1.76 times 10 to the 8. C is a coulomb. It's a unit of electrical charge per gram. So coulomb is charge and grams mass. So charge to mass of an electron is what we're looking at. There he is staring at his tube. I don't think parents say that anymore. They used to say years ago, not good. It's like shooting things at you. Don't sit in front of the TV. They were actually kind of right. They were shooting those things at you. So this is one really big sort of step in terms of understanding really sort of the structure of electrons. So you do need to know Thomson. Do you need to know he used CRT tubes to explore sort of electrons. And you do need to know that the result of that was he was able to figure out the charge to mass of an electron. Any questions on that? So further sort of experiments were done to sort of explore electrons, and the next kind of major electron sort of experiment was one done by Milligan. It is sometimes referred to as the oil drop experiment. And it is pretty much what it sounds like. He took oil and he sort of atomized it and droplets of oil, and he put it into a chamber. And as the oil would come in, it would fall, the little droplets, based on it dropping, it would kind of gain up a charge. And he was able to use the electrical field that was in this chamber and adjust it in such a way that it was able to kind of suspend basically the oil droplet there because of the charge. And let's take a look at that, maybe play. Maybe. So that's the oil droplet. And again, he was able to really kind of adjust it there. And basically, it just kind of hung there. And from that, what he was able to basically sort of determine is the charge of an electron. So Milligan, through his oil drop experiment, was able to assess the charge of an electron, which is minus 1.60 times 10 to the minus 19 coulombs. So these two experiments were really big for sort of the understanding of the electron. So if you think about Thomson's experiment, where he had the charge to mass of an electron, so Thompson did the charge to mass, and here Milligan was able to figure out the charge of an electron. If you sort of put the results of both of those experiments together, if you take the charge and you divide it by the charge to mass of an electron, the charge cancels out, and you're able to basically determine the mass of an electron. So sort of putting both of these experiments together, the mass of an electron was able to be determined, and that is here. And the mass of an electron was found to be 9.09 times 10 to the minus 28 grams. Is that a large number or a small number? That is a small number, yes. That is 28 places to the left and add a bunch of zeros. Yeah, so it's a super small number. So those are the two experiments so far that you need to know. Thomson CRT tube, charge of mass coming out of it. Milligan oil drop experiment, charge of it. And you need to know a little bit about the experiment. And again, putting both of those together, what truly came out in terms of the understanding of our negatively charged electrons was the mass of it, which was 9.09 times 10 to the minus 28. Any questions on that there? So at this point, there was always sort of an idea that the atom itself was neutral. And obviously, it did contain electrons from these early experiments. So if it has to be neutral and it contains these negatively charged electrons, it has to have something, obviously, that is positively charged to sort of balance it out. So around the turn of the last century there, the accepted model of the atom was one that was proposed by Thompson and is sometimes referred to as the Plum pudding model of the atom. And basically, his model of the atom was that the atom was basically the sphere of positive charge, really sort of spread out all over it. And sort of embedded inside the sphere of positive charge were these electrons. So it had these electrons sort of embedded, kind of like the dessert. It's like a pudding with raisins in it. So it's like, oh, that's the atom right there. Yeah. Could have been eating a pizza and it would have been a whole different model, I suppose. So that was his idea. And really a major part of that was he felt that it was actually the electrons that made up most of the mass of the atom. So this was really sort of the accepted model of the time. We got all this positive charge sort of spread out all over it. We got these sort of electrons sort of embedded inside of it. And pretty much, the electrons is going to be really the most massive part of an atom. There's a much better picture than what I drew. And this was really sort of the accepted version until the next sort of really big experiment happened, and that was Rutherford and the gold foil experiment. So Rutherford, along with some other people like Geiger, like the Geiger counter guy, radioactivity, They studied the structure of the atom using alpha particles, and alpha particles are basically radioactive particles. There's kind of three major sort of particles that are oftentimes used in these type of experiments. There are alpha particles, which is that abbreviation there. And alpha particles are radioactive particles that are really positively charged. Frankly, they're helium, basically, is what it is. And so you'll sometimes see the symbol like this. There's also beta particles. And beta particles are negatively charged. And, they're thought of as kind of being like an electron, basically. And there's also gamma rays. And gamma rays basically have no charge. So you can kind of see a lot of these sort of three radioactive particles, which is used in a lot of experiments. They sort of replicate, if you will, the three particles that we sort of find in the atom. Alpha particles being positive, like protons, beta being negative, like electrons, and gamma having no charge, kind of like neutrons. So they're sort of very similar. So what Rutherford did was he took pieces of gold foil and really other metals, and he basically shot alpha particles at it. So he had this idea of the atom that Thompson sort of came up with, which was this plum pudding model where we have all this positive charge spread out. We have our electrons that are embedded inside. And he was going to basically shoot up here some alpha particles at it. And I'll go with blue. Which again are positively charged atoms. So what he expected to happen was, if I were to shoot these positive particles at this atom that is basically positive charge all spread out. So for example, let me destroy this paper. Do I need it? Yeah, just a 10 minutes. Who needs power? So let's just say my atom is now 8 by 11 or whatever this paper is here. So this is my atom and it's all positive charge basically spread out all over it, right? And if I were to say hold the paper or the atom here on one side, somebody else was going to hold it really, really tight on the other side. And if this was my alpha particle, right, and I shot it through, right, really fast, it probably would be able to punch through, right, with some deflection. And we're going to have some deflection, right, because we're shooting something that's positive at something that is positive. But this positive charge is pretty much spread out all over the place, right? So it won't be able to punch through because it's heavy, it's moving fast, but it will kind of maybe deflect a little bit as it went through. So what he thought would happen when he did this is he would shoot these and, we would see some deflection that would basically occur because they're heavy, they're moving fast, they're going to kind of punch through the positive jelly layer of the atom. And he was actually surprised when he did the experiment. He found that pretty much when he shot the alpha particles, most of them, as badly drawn as that is, went through undeflected. Imagine that's a straight line. So they went through undeflected, just kind of, sailed through, no problem. But they did notice that every now and then they would see an alpha particle sort of scatter at really large angles. So it would kind of go out in these kind of weird angles, even come back to the source. So that was really surprising to him because these alpha particles are heavy, they're moving fast. So in order for those guys to bounce off at these really, really large angles, what did it have to hit? It had to hit something that was what type of charge? Very positively charged. If it was negatively charged, it would stick, right? I'm happy here. I'm not going to go through. I'm just going to stick right here. But because it bounced off, right, it had to be something that was very, very positively charged to make it do that. How come they all sailed through with no problem? Those things hit nothing, right? So if I threw my pen there, there's nothing in the way. It's just going to fly, right? But if I throw my pen now, if I take my atom that had the positive charge all spread out and go, all right, well, maybe that's not so correct. But if I then took my atom with its positive charge and I sort of folded it, right? Where they say 7 times is how many times you can fold a piece of paper before you can't go any further. and I take all my positive charge here. Well, I'll go that way. And now my positive charge is all concentrated here. When I send my alpha particle at it, right, it hits something that is not going to go through. It's going to bounce off because it's the same charge. So that totally meant that, you know, although Thomson had this model of the atom that we saw there, the plum pudding model, is not so correct based on the results that we saw from Rutherford's experiment. So we had to sort of throw out, I mentioned the results of this, as you can kind of see in the video here. I apologize about the sun coming down, but you can see there's all this scattering that's happening, but a good majority of them just sailing right through. So basically his findings were, as we talked about, that, you know, we have these guys coming out these large angles, kind of like shooting a gun at a piece of paper and the bullet coming back. It had to hit something super dense at it. And they had to sort of abandon that early model and explain sort of the new model of the atom and really the modern model of the atom, that based on Rutherford's finding, the atom is really mostly empty space. And as we know, in that empty space is pretty much where those electrons are basically flying around it. And that accounted for why pretty much all those alpha particles sail through, no problem. It also has a very dense positive core, which was called the nucleus. And later experiments found that inside the nucleus, protons are found there. And later in like 1930s, neutrons are found as well in the nucleus. And another very sort of major difference between the modern version of the atom and Thomson's plum pudding model is, in Thomson's model, he felt that the electrons were the one that made up most of the mass of the atom. And in Rutherford's sort of model, and the modern model, is the atom is mainly, atom's mass is basically the nucleus. So the nucleus basically makes up most of the mass of the atom. And we'll talk about why that is next time, I suppose. Any questions on anything we talked about here? All right, we will lay it up there.